Hi everyone, thanks for having me here. My name is Shiden. I'm a software engineer at WhatsApp. Today I want to talk about private calling at WhatsApp. At WhatsApp, our mission is to connect the world privately by designing a product that's simple and private. Privacy and security is in our DNA. According to our blog, we have 2 billion people around the world use WhatsApp. They spend 15 billion minutes talking each day on WhatsApp calls. At such scale, the responsibility and the challenge is huge to us. Here's the agenda. Firstly, I want to briefly talk about our understanding about privacy. Then we will go through the private one-to-one call, then our private group calls. Privacy. So what are considered private information in calling? I want to go through some examples with the 4W and 1H way. First, what? Typically, audio and video conversation content are considered in this type. Second, who? Those are the participant or membership who are in the call and their personal identifiable information. And where? The information which may tell participants' location, such as IP address, and when the call is started or ended, and how the call is communicated. Is it an audio call or video call? There are more private information in calling. Those are just examples. And who should we protect the user privacy against? What are the adversaries? We have 3 categories. The first category is third party, which includes network infrastructures and telecom service provider. Those are not trusted. The second category are service provider, including Meta and WhatsApp, which provide calling service. Those are trusted. And the third category is most trusted. Those are the call participants who are in the call. But even in this category, there are some risk. For example, there are 2 subcategories. The first one is peers. Regarding peers, if I have muted my microphone or camera, I don't want to leak my content to peers. Another special case is a stranger peers. When I receive a call from a stranger peer, I don't want to leak my location to them. The second category is one's own device. As we are rolling out multi-device, user can use WhatsApp on several devices simultaneously. Theoretically, when users are on a call on one device, the other device may be used by their family, so we don't want those devices to be able to intercept a call happening on the other device. So what are the challenges and general method? The biggest challenge is that we attempt to use the data while protecting it. Some data usage are actually inevitable. For example, we have to use recipient's IP address to forward the media packet and the signaling message. Another example, we use insensitive audio-video matrix to monitor and improve our call quality. At the same time, we want to protect data. For example, we don't want to leak users' PII, we don't want to leak users' audio-video data, but how to protect those data? Here are the general methods. The first method or principle is minimal use or stored data. The less data we use, the more security we are. If we have to use or store data, we need to keep the data confidential. And we also want to apply retention so we can delete the data after some time. Another technology is anonymized data. Once the data is anonymized, even in the worst case, even it's leaked, there's no way to track back to a certain user. Okay, after the general understanding of privacy, let's talk about our private one-to-one call. As mentioned, our principle is use as few data as we can. So we use client-centric architecture in one-to-one call as we can. In one-to-one call, each client connects to a signaling server and to send or receive their signaling. We avoid state in the signaling server to minimize the data usage. Another benefit is that we can avoid failover for calling state. This also helps scalability. Almost all signalings are just passed through our server. The call state and the data is stored in our client side. For example, the call history is populated and stored in the client side according to the signaling it sends or receives. Besides the signaling server, we also have relay server to help net traversal. So in setup signaling, the signaling server will deliver relay info to clients. Then the clients will use those info to bind to our relay servers. And those info are designed with insensitive data to minimize data usage. For example, there's no PII. So in this way, the relay server are decoupled from signaling server for minimize data usage. And this is also mitigate the need of failover for better scalability. To achieve better connectivity, we deliver multiple relay server candidates to clients, and the clients use consistent distributed algorithm to elect the best one for connectivity. Once relay is set up, we also try to set up peer-to-peer data channel for minimal latency for media packet. However, if a caller is a stranger, we may disable P2P. It will introduce longer latency, but we believe that's better to protect callee's location against the caller. In both relay and P2P case, the media data is end-to-end encrypted with SRTP, so we can protect the content against the third party and also WhatsApp. SRTP is open standard, which uses a shared master secret and a symmetrical encryption to protect data. So the key to achieve end-to-end encryption is to exchange the master secret in an end-to-end encryption way. To do this, we rely on our end-to-end encryption messaging channel, which is built on top of Signal protocol. Signal protocol is a de facto standard which is broadly used by apps. In our case, we let caller generate the master secret and send it through end-to-end encryption channel to the callee side. So caller can immediately start media decryption once it receives media packet from callee side. This can reduce the latency. In multi-device world, the caller will generate different master secret for each callee device. By this way, we provide actual protection. Once the call happening on one callee device, other callee device cannot intercept the conversation. End-to-end encryption is beautiful, but it has a well-known problem, which is man-in-the-middle attack. Let's see example. See, our server is hacked by some hackers. In this example, Alice sent master secret to Bob. However, the hacked server can pretend as a fake Bob and ask Alex to reset up the end-to-end encryption channel and reset the secret mask. On the other side, it can also pretend as a fake Alice and reset up the end-to-end encryption channel and send the master secret to the Bob. By this way, the hacker will get the master secret and use it to intercept the conversation between Alice and Bob. How to address this problem? We rely on identity. We adopt trust on first use mode. For the first time, Alice and Bob became a friend. They will just trust each other's identity. They can verify security code in person to make sure those are authentic Bob and authentic Alice. And afterwards, if end-to-end encryption channel is changed, identity change will happen. And if user has turned on the security notification, they will notice the identity change and they can verify the security code in person again. However, not all identity change are man-in-the-middle attacked. In fact, most of them are legitimate. For example, it may happen when user reinstall the app. If that happens on a phone, we will auto set up the end-to-end encryption channel and auto send the secret mask to provide a seamless call experience. User can still find the identity change in the chat if they have turned on the notification. But when this happens on a companion device like a desktop, we will block the call because we think that's not a legitimate case. Okay, I've talked about the general architecture and then end-to-end encryption. Let's talk about some challenges in our architecture. Because we use client-centric architecture, we don't have a central server with central state to address conflicts. so we have to rely on the client solution. Let's see a fixed example, multi-device. In multi-device, the callee may have several devices, they may ring at the same time, and technically they can accept calls simultaneously. How do we address this conflict? Let's see the diagram. In this example, Alice calls Bob, and Bob has two devices. When Bob accepts call on device 1, the device 1 will send accept to caller and also other device of Bob. So if other device haven't sent accept, they will just end the call because they know device 1 has accepted. However, if some device also accept the call, both of the device 1 and that device will go to pending state, and they will wait for the caller device to make the final decision. The caller Alice device serves as a single source of truth here. Once it receives the first accept from any of the Bob device, it will send the terminate to other device to break the tie. By this way, we maintain the consistent state among all the devices. Another example is the audio-video switch. To provide better user experience, we allow user to switch between audio call and video call in the same call. However, when user upgrade from audio call to video call, we require peers' consent. So in this case, we don't have a central state in the server side to judge if the call is audio call or video call. There will be lots of conflicts, and we still rely on client solution to address it. Let's take an example as a diagram. In this example, Alice and Bob are in an audio call. Alice requests to escalate to video call, and Bob is okay, he accepts the call. However, Alice changed their mind. Alice canceled the request, want to go back to an audio call. Okay, at the moment, both sides has different state. How do we adjust that? We rely on the privacy order. We consider audio call is a higher priority than video call in both sides. So let's look at Alice's side. Alice goes back to audio call after she canceled the request. Then she received the accept from Bob. Because audio call is higher priority than video call, Alice will just ignore that accept. On the Bob side, Bob will shortly go to video call after she accepts the call. However, once Bob received the cancellation from Alice, because audio call is higher priority than video call, Bob will revert back to audio call. So by this way, we maintain the eventually consistent state in both sides. Let's recap the one-to-one call. First, we make the content confidential by using end-to-end encryption. We protect that against third party and also WhatsApp itself. We improve our master secret exchange for better user experience and security. Second, minimal use or store data. We use stateless signaling server. We use decoupled release server to minimize the data usage and to achieve less failover for better scalability. Third, overall architecture is client-centric. Client runs consistent algorithm to handle all the conflicts, to mitigate the need of data in the server side. We also provide actual protection against peers, strangers, and non-active device. Okay, let's talk about the private group call. Group call has more participants than one-to-one call. It's very hard to handle some conflicts with only client solution. For example, we currently allow 8 people to connect to one call. Say a call already has 7 people connected, and 2 people want to accept call at the same time. How do we address that conflict? To address all these kinds of hard conflict, we added centralized logic and transition cross-state storage to the server side to help solving the conflict. The state will be removed after call is ended or timeout. Besides addressing the conflict, adding the central state in the server side can deliver the client state to all participants, so client can get information of other participants from server with half of RTT, and it can avoid ON square information exchange, which saves bandwidth and latency. On the other side, we still use client logic for something else. For example, the call history is still populated and stored in the client side. In group call, for better media quality control, we upgrade our relay server to Slack forward unit. We also added simulcast support. The setup flow for SFU is still similar as one-to-one call. The SFU server is still coupled from the signaling server with minimal setup information. And we still run consistent algorithm in the client side to select the best SFU server for all the clients. The data in group call is still end-to-end encrypted by SRTP among all the user pair. To better control the media quality, we introduced the WhatsApp real-time protocol. It has a compact header. It can be pitched back with SRTP. It can provide both hop-by-hop and end-to-end media control. There's no P2P in group call. Everything will go through the SFU to minimize the bandwidth usage of each client. The master secret exchange in group call is different from one-to-one call. Because group call is complicated, there are membership change, say people join and people leave. We don't want to leak the content to the participant who just joined or who just left. We use a session key mechanism to exchange the master secret. By this way, whenever is a membership change, a remaining participant is selected as a generator. The generator generates and dispatches the new master secret through end-to-end encryption message channel to everyone else. After everyone gets the new master secret, they will start to encrypt the media content to achieve the end-to-end encryption. The solution is very simple. It has minimal signaling exchange. The complexity is ON globally, and it's just one message per participant. It's easy to scale for large group call. For security, the generator only dispatches the secret to active device if one user has multiple devices. Since the master secret is dispatched in an end-to-end channel among each pair of devices, the identity handling is similar as one-to-one call. Let's recap the group call. For group call, we are doing more things in the server side for scalability. We added the central control, we added the centralized storage to handle conflicts and to optimize the user experience. And we also use session master secret mechanism for better scalability. Overall, we use a hybrid architecture. We leverage client-centric algorithm whenever it's still feasible to minimize the data need in the server side. But when the benefit is huge, we rely on server solution. If you want to learn more, please take a look at our security page and the white paper. Thank you everyone, and join us to help billions of people to connect privately. You can find me on LinkedIn. Thank you.